Hello everyone. So this is our tutorial 7, and in this tutorial we will be studying the thermodynamic and transport properties in plasma. So basically we will review the kind of transport and thermodynamic properties that we have studied in our regular classes. Then we'll try to understand some the summary of the key features of this transport and thermodynamic properties. Then we'll do some numerical problems. So the topics that we'll be considering in this: the partition function hierarchy, then thermodynamic and transport properties, summary of the key features, then some elementary ideas on variation of properties of the common plasma gases with temperature, pressure and chemical non-equilibrium. Then we will go for some numerical problems. So we start with the first one, that is the partition function hierarchy. So the total partition function is basically product of translational, this one, rotational, vibrational and electronic partition function. Now, while you have studied most of them in your BSc or MSc classes, I would like to just summarize the results that you can so that you can memorize the final results. So the translational partition function goes like this: b 2 pi m kt by h square to the power 3 by 2. This kb is the Boltzmann constant and v is volume. So this is rotational partition function. So if you are able to a characteristic rotational temperature, to find a characteristic rotational temperature, then it is very easy to write the rotational partition function quite accurately using this formula. Of course, this happens when T much greater than rotational temperature. So that time it can be well approximated using this formula. And then vibrational partition function goes like this as a function of temperature. And electronic partition function, which contributes the most in case of your monoatomic gases, atomic transitions. So that goes like this one. So it is sum over the states. And here, as I already told you in the regular classes, the major thing is to find all the energy levels. So whatever is appearing here, and an atom or an ion can have can easily have number of levels more than 400, 500. So finding this sum is not as easy as it looks, because for each level you need to know the degeneracy and you need to note the exact values of the energy of that level, and there are 400 levels. So noting down each of the level as energy is not a very easy task. But again, if you note down say 100 columns or say 200 columns, you know how painstaking it is. So when you go for say 400, 500 energy levels, first of all finding all the levels is one task, and then putting that in your program to get the partition function estimated is another task actually, and writing them accurately, error free is another thing. But it is of course, a laborious task, but the amount of labor that you need to put got simplified nowadays with advent of these websites. There are NIST websites where all these energy levels are actually listed for most of the you know atoms and molecules even. So, for that it is rather easy to go to those sites and you can just directly copy those energy levels, and then you can use those in your program. Those data are freely available so far, so that can be used. You need to acknowledge the site where from you have received that data. So, and those data that has been compiled in that website has been taken from the literature. Here only advantage you are getting that you don't need to go to individual literature where from all these energy levels are tabulated there, but all the references you will be getting over there, so it's not a problem. So this is what actually your electronic partition function that you can calculate. So once you know this translational partition function, rotational partition function, vibrational partition function, and electronic partition function, this is basically applicable when you are handling a molecule. When you are handling atom, of course there is no rotational and vibrational, so you will have translational and electronic transitions partition function. So you can just multiply these two and you can get the total partition function. But in case you are handling these molecular gases, then you need to multiply all those, that is translational, electronic, vibrational and rotational all together, that give you the total partition function. So in this partition function hierarchy, to find the find the thermodynamic properties, the first thing is to accurately estimate the partition function value as a function of temperature. Once you know the behavior of Z as a function of temperature, then you can proceed further to find out the thermodynamic and transport properties. Because for composition you will require this partition function, and this composition actually determines the transport properties as well. So once you know the this partition function, then from our knowledge that we acquired in our BSc or MSc classes, we know that how to find out the internal energy for the system once you know the partition function. So here how it goes, the internal energy U can be calculated as kBT square del T of log of Z. Okay, so that is one thing done. Once you know the variation of this partition function as a function of temperature, obviously you can do this thing. But one thing let me tell you that this behavior of Z as a function of T may not be in closed form. In most of the cases you will be getting a relationship of Z as a function of T that is not having any closed form. So if you want to find out del T of log of Z, then you need to go for the numerical technique most of the cases. So if you want to proceed with the computation of these properties, then you must be very much familiar with numerical techniques, how to do the integration, how to do the differentiation, what are the finite difference techniques, what are the finite volume techniques. So elementary ideas you should have, because this partition functions theory you require here to get the derivative, and getting a numerical derivative requires a bit of experience, otherwise you will not get, these are all delta T is an elementary quantity, but that again depends on the kind of parameters, their magnitudes that you are handling in the system. So you need bit of experience in finding these derivatives numerically, but that is not at all very difficult, you can do it easily. So once you know the variation of Z as a function of temperature, you can find out the internal energy using the first formula. Then comes the specific heat. Once you know the U as a function of temperature, then you know that del U del T V will give you the specific heat at constant volume. Similarly, you can find out the specific heat at constant pressure. Now, from the partition function, the variation of pressure as a function of temperature you can find out using the formula that is written over here. Now, the entropy you can again calculate from the partition function using this formula, and Helmholtz free energy you can get from this one. So, essentially what you are getting here, so if you have already noted that we are getting everything when you know the variation of z as a function of temperature. So, that is the key of the everything here. So, once you know the partition function, basically you are able to derive all these thermodynamic parameters very easily. Okay. So, with this actually I now go to the transport properties. So, what are they? They define the momentum, energy and mass transfer through the plasma, and that is very important as far as application is concerned. You definitely want to impart momentum, energy, or you want to go for this mass transfer for the process that you are handling. So, as far as this process is concerned, transport properties are very much important. And you know that how to find out the transport properties, that we have discussed already very well in our regular classes. Here what we summarize what are they. So, they depend on the collisional kinetics. You need to know the collision integrals, collision cross sections, and of course the interaction type, what type of interaction it is doing. So, whether it is a charge-charge interaction, definitely it will be done through your Coulomb kind of interaction, whereas if you are interacting with molecule-molecule neutral interaction or neutral charge interaction, or that those interaction will be in a different type of potential. So, once you know the kind of potential through which they are interacting and the collisional kinetics, you know the collision cross section, collision integrals, then you can take the help of kinetic theory and basically the Chapman-Enskog approach to find out the transport properties. So, those things we have discussed well in our classes. So, basically they depend on the collision kinetics and the interaction type. So, with that we can tell what are the coefficients that we are mostly interested in. So, one is viscosity, the transport properties. So, what things it transport? It transports momentum, viscosity one. Then we come the thermal conductivity. What it transports? It transports energy. Then diffusivity, what it does actually, this is one diffusion coefficient, is another transport coefficient. So, there are a number of diffusion coefficients that we have discussed elaborately in our class. So, what it does, diffusion causes the particles to diffuse from one place to another because of the gradient in the number density. So, that basically transport mass. Then we come to the electrical conductivity. What it does actually, it gives transport of charge. So, all these transport coefficients like viscosity, thermal conductivity, diffusivity, electrical conductivity, they transport something or other, maybe it is momentum, energy, mass or charge. So, they are related to those. So, this just summarize the thermodynamic transport properties. How do we get that from the partition function hierarchy, and the transport properties, how are they calculated and what they transport. So, this is the thing. Now, I enter into one numerical problem. So, this is the 19th numerical problem that we will be solving now. So, the problem says that Einstein relationship for electrons and nitrogen ions can we verify from the data. Electron mobility, electron diffusion coefficient, nitrogen ion mobility and nitrogen ion diffusion coefficients are given. Now, what Einstein's relation says that d by mu is equal to kt by E. So, what are the quantities? D is the diffusion coefficient, it is in meters square per second. Mu is the mobility, so velocity per unit field strength, that is the quantity mobility. Now, K is the Boltzmann constant that and T is the absolute temperature, and Q is the charge of the species. So, D by mu is equal to KT by E. So, you just don't get confused with mu and mu and the viscosity, that is also uh, usually the symbol mu is also used sometimes there. So, you just don't get confused with that. This mu is the mobility here in the Einstein's relationship. Okay, what is there? Now, what we need to know, what we need to do actually, that the Einstein's relationship whether is holding well for the kind of data that we have obtained over here. So, let us look at the magnitude of the data. So, electron mobility is given as 1060 meter square per volt second. Then this electron diffusion coefficient is given as 27 meter square per second. Then nitrogen ion mobility is given 0.15, and the same this diffusion coefficient is given as 4 into 10 to the power minus 3 meter square per second. Now, the things to note is that you just note the difference in the electron mobility and the nitrogen ion mobility, the data that is displayed over there. So, you can compare, one is in the range of 1060 meter square per volt second, the other one is just 0.15. You can see the order of magnitude difference, it is 4 order of magnitude difference is seen almost like that. And regarding the ion diffusion coefficient and electron diffusion coefficient, you see again you are seeing one is 27 and one is of the order of 10 to the power minus 3. So, again a 4 orders of magnitude difference is there. So, that is something you should need to realize actually, the mobility of the electrons. We always say that electrons are much higher, have much higher mobility compared to the ions, but how much higher? Okay. So, these ones tell you that thing, like say always say that electrons are lighter than the proton, but how much? So, those things you need to keep in mind actually. So, here you are seeing that almost 4 orders of magnitude difference is there when you are comparing the electron mobility and ion mobility, and the same for diffusion coefficient when you are comparing the similar kind of order of magnitude difference exists there. So, that is basically the purpose of this tutorial, to bring out the underlying features in numerical form or in exact values, and to put in your the notion or in your idea that it keeps in your mind, it strikes you that this is the kind of difference that is there in the transport parameters. So, for electrons, what we are getting, that d is 27 and mu is 1060. So, d by mu is 27 by 1060. So, it is coming to be 0.2547 volt, it is coming here, d by mu. Then kt by q is coming, you can that what are the parameters, and what we are getting here, that kt by q is 0.025875 volt. So, you can see that up to third decimal place they are matching with each other, at fourth decimal place they are differing. So, these are anyway experimental values. So, we can say that Einstein relation holds well for electrons. Now, it comes the ions, nitrogen ions. So, for that we got that mu by mu is 0.15 and di is 4 into 10 to the minus 3. Both are quite less compared to the electrons. So, these are the electrons, this mobility and diffusion coefficients, and here the same for ions. You can see the how low they are. So, but d by mu, the ratio is again it is coming to be nearly same, it is 0.02667, and when you calculate the kT by Q, it is it is always because the same temperature, so you are getting the same value as previous one. And you see that although there is a wide difference in the mobility and diffusion coefficient values in one species compared to the other species, but d by mu is same for both. So that is the striking thing. So d by mu depends on kT by E. Okay. So if your temperature is same and the ionization is a fast ionized states only, then if your diffusion coefficient is less, then mobility is less, diffusion coefficient is high, mobility is high, similar, the vice versa actually. So d by mu remains the constant. Now regarding ambipolar diffusion coefficient, this dA is this another problem where this or numerical 20th, where we want to prove that the relation for ambipolar diffusion coefficient, which is dA is equal to d mu I plus di mu e by mu I plus mu e, we want to show that when Te is much greater than Ti, like in the non-equilibrium plasma, then dA is basically governed by the heavier species, that mu I, okay, diffusion. And when they are comparable, like in the thermal plasma, then ambipolar diffusion coefficient is just twice the diffusion coefficient of heavier species. So in both the cases, what we are seeing that the heavier species basically controlling the diffusion, ambipolar diffusion. So let us go to this thing. So from Einstein relationship, we know that d is this one and di is this one and dA is this one. Okay. So if we put the dE value over here, then and di value over here, then what we get? This expression we get. And what we finally get? D is equal to mu e mu I by mu I plus mu e kT plus Ti by Q. So when T is much greater than Ti, the first case, what we see that mu e is much greater than mu I. So what we can get from here? You just divide mu e both numerator and denominator. In the top you will get mu I, and at the bottom you will get 1 plus mu I by mu e, because mu e is much greater than mu I. So this you can neglect compared to 1, then you get this one very easily. So kT by E mu I. So the first relationship that you wanted to have. And when your they are comparable, T equal to Ti, but mu is much greater than mu I, it is always true. So then what you get actually, T of the order of Ti equal to T, then what you get? This relationship you finally get. So twice mu e mu I by mu e plus mu I kBT by Q. Now this one, when mu e is much greater than mu I, you get again same thing. So you get mu I by 1 plus this thing. So twice mu I basically kT by Q. Okay. So this is mu I kT by Q is what? This is the di. So you get when T is of the order of Ti and mu is much greater than mu I, dA is just twice. This factor is there and this goes to 1, and mu I is there, and mu I kT by Q defines the di. So you get dA is equal to 2 di. So this what we just wanted to show, we have obtained here. The fact is that the ambipolar diffusion is controlled by the heavier species. You see that this is di and this is mu I. So and they are they are basically defines the diffusion of the whole species, because this is ambipolar. Ambipolar means the electrons and ions both are getting drifted in the same way, but what will be the diffusion rate? So in one case, when T is much greater than Ti, this is basically controlled by Te. You see that T is over there. And this is T and mu I is of course there. And when it is thermal, the diffusion is basically controlled by the ions, because ultimately they both need to move together, and the heavier species is basically controlling the diffusion. So with this I stop this tutorial, and in the next tutorial will be in the next class. So see you there. Thank you.